Welcome to this first video of my playlist about the hydrogenation of arenes to cyclohexanes. This presentation is about the heterogeneous catalytic hydrogenation of substituted arenes. In part 2, we'll have a look at the homogeneous version of this reaction. For a more detailed discussion of the advantages and disadvantages of supported and soluble catalysts, you can check my playlist about the hydrogenation of alkenes. There you'll also find a more thorough discussion of potential side reactions. Because hydrogenations do not generate any waste and hydrogen is relatively inexpensive, arene hydrogenation is used industrially for the large-scale production of important commodities, mostly monomers for the production of polymers. Benzoic acid, readily available by oxidation of toluene, is hydrogenated on a large scale to cyclohexane carboxylic acid. The latter can be converted into epsilon caprolactam by alpha nitrosation and decarboxylation with nitrosyl sulfuric acid. Caprolactam, the starting monomer for the production of nylon, can be prepared by Beckmann rearrangement of cyclohexanone oxime, which in turn can be prepared by hydrogenation of benzene or phenol. Cyclohexanone is also a valuable starting material for adipic acid and diaminohexane. Also dimethyl terephthalate is being hydrogenated and reduced to bis-hydroxymethyl cyclohexane, one further monomer for polyesters and other polymers. Arenes are best hydrogenated with supported rhodium or ruthenium catalysts. These catalysts show the highest selectivity for arenes while leaving most other functional groups untouched. Other common hydrogenation catalysts, though, can also be used to hydrogenate arenes. For instance, platinum, palladium, nickel or cobalt. The selectivity of these reactions can often be modified by the choice of metal and solvent. For instance, hydroxyacetophenones can be reduced to cyclohexyl ketones, carbenols or alkanes by varying solvents and catalysts. With ruthenium on alumina in THF, it is possible to keep the ketone unreduced, but few examples of such reactions have been reported. Typically, also the ketone is hydrogenated, as shown in the second and third equation. Then, under mild conditions, it is possible to stop the hydrogenation of phenols at the cyclohexanone stage. Because the rate of hydrogenation of arenes depends on many factors, it is not easy to establish a universal scale. In general, naphthalenes and other polycyclic arenes and heteroarenes, such as indoles or quinolines, are hydrogenated faster than monocyclic arenes. Because in naphthalene, for instance, only one ring is truly aromatic. Thus, the hydrogenation of naphthalene to tetraline is fast, with a low barrier of activation, while the hydrogenation of tetraline to decaline is much slower. Then, benzoic esters tend to be hydrogenated faster than alkoxy or aminobenzenes, and these, in turn, faster than alkyl benzenes. Pyridines are also hydrogenated faster than alkyl benzenes. The rate of hydrogenation of benzoic acids, anilines, pyridines or quinolines, though, can also be impacted by the addition of acids or bases. Let's have a look at some specific examples. Aryl halides are difficult to hydrogenate without reductive cleavage of the carbon-halogen bonds. Trifluoromethylarenes, however, can be hydrogenated selectively. Here, for instance, a trifluoromethylphenyl group and a benzyl group were hydrogenated without reduction of a pyrrole. No extensive debenzylation occurred. Phenols can be tricky to hydrogenate. These reductions proceed by intermediate formation of enols, which can rapidly tautomerize to ketones. Not all catalysts suitable for arene hydrogenation do hydrogenate ketones readily, and one potential byproduct of these hydrogenations are therefore ketones. Palladium, for instance, is not particularly good at hydrogenating aldehydes or ketones. In this example, hydroquinone was hydrogenated with palladium on charcoal at 160 degrees Celsius, and a fair yield of 4-hydroxycyclohexanone resulted. In this example, 2-benzylphenol was hydrogenated with the aid of a supported cobalt catalyst. Again, a high reaction temperature was required. The benzyl group remained mostly unaffected. 1,2-disubstituted arenes are often hydrogenated with high cis selectivity, but as shown here, this is not always the case. Not all phenols are hydrogenated faster than non-phenolic phenyl groups. Here, the hydrogenation of a phenyl-substituted binaphthol with palladium or ruthenium catalysts yielded exclusively a cyclohexyl phenol. The reason for this was probably poor steric accessibility of the phenol rings. The selective hydrogenation of anilines in the presence of alkyl benzenes is also possible. Here, with a platinum catalyst and in the presence of acetic acid, anilines were reduced faster than benzylamines. With a cobalt catalyst, though, this selectivity could be reversed. Thus, in cases like this, it is worthwhile to test various catalysts, solvents, and additives to improve selectivity and yield. In this example, a substituted aniline was hydrogenated in the presence of a pyridine. A large amount of supported rhodium was used as catalyst, and the hydrogenation already proceeded at room temperature, without any hydrogenation of the pyridine ring. Aminopyridines, by the way, are catalyst poisons, what may have been the reason for the large amount of catalyst. Here, a selective hydrogenation proved to be more difficult than in the previous example. With rhodium, mostly the aniline was reduced, while with palladium, a substantial fraction of the alkoxyarene was hydrogenated. If compared to trifluoromethyl groups, trichloromethyl groups are chemically more reactive. In this example, a dihydroquinoline with a trichloromethyl group could not be hydrogenated selectively without partial dechlorination. The hydrogenation only proceeded when using a large amount of platinum oxide as catalyst. With palladium on charcoal, almost no reaction occurred. When carbon-halogen bonds undergo hydrogenolysis, hydrogen halides are formed which increasingly acidify the reaction mixture as the reaction proceeds. In such instances, one should try to use a basic or acidic buffer to keep the reaction mixture alkaline or acidic throughout the reaction. It is usually much easier to find the optimal catalyst and solvent for a reaction run at a constant pH than for a reaction with a strongly increasing or falling pH. Polysubstituted arenes can sometimes be hydrogenated with remarkable cis selectivity. In this instance, an intermediate for the preparation of oseltamivir was obtained by hydrogenation of a trialkoxy isophthalate with a supported ruthenium catalyst. Few examples have been reported of the hydrogenation of acetophenones or benzaldehydes without simultaneous reduction of the carbonyl group. With ruthenium catalysts, this occasionally works, as in this example. The stereoselectivity was much lower, however, than in the previous example. At a slightly higher temperature than in the previous example, the same catalyst led to a complete reduction of the ketone. It is unclear if the long reaction time really was necessary here. Benzylic amines occasionally undergo debenzylation during catalytic hydrogenations, in particular in the presence of acids, and optimization may be required to prevent this dealkylation. Here, an N-benzyl acetamide could be hydrogenated without debenzylation with a ruthenium catalyst in THF. In this example, an oxime was hydrogenated to a benzylic amine with a large amount of platinum in acetic acid as solvent, but no extensive deamination occurred. Here, the benzoic acid substructure was hydrogenated faster than the electron-rich dialkoxyarene. Benzylic alcohols and their derivatives undergo CO bond cleavage more readily than benzylic amines. Under optimized conditions, it is however possible to hydrogenate the arene of benzylic alcohols and obtain good yields of cyclohexyl methanols, as in this example. Again, platinum was used as catalyst in the presence of acetic acid. Here, the starting material was structurally complex, with 3 benzylic ethers and a Weinreb amide, and the authors struggled to achieve a selective debenzylation. With rhodium, the phenolic ether was cleaved, but one benzyl group was hydrogenated to a cyclohexyl group. With Raney-nickel, no aromatic hydrogenation occurred, but the Weinreb amide was cleaved. With palladium in toluene, however, the selectivity of debenzylation was reversed, and the Weinreb amide remained unchanged. Screening of various solvents revealed a rather peculiar ranking in this specific case, but in general, less polar solvents tend to slow down debenzylations, while highly polar ones combined with strong acids will accelerate debenzylations. Also, epoxides, even non-benzylic ones, are readily cleaved under the conditions of catalytic hydrogenation, in particular with palladium and platinum catalysts. Under suitable conditions, it is though even possible to hydrogenate arenes in the presence of epoxides, as in this example. Here, rhodium was the catalyst and the hydrogenation was conducted in THF. This is an example of the troublesome hydrogenation of an aminopyridine. Huge amounts of catalyst and repeated filtering of the reaction mixture and cleaning of the reactor were required to attain complete conversions. The authors couldn't identify the catalyst poison, but the fact that washing the reactor with hydrochloric acid helped points towards some amine, probably the deprotected aminopyridine. 4 aminopyridines are highly nucleophilic and therefore good catalyst poisons. Unfortunately, conducting the hydrogenation in pure acetic acid still was slow and required large amounts of catalyst. In this example of pyridine hydrogenation, only 2% of palladium was sufficient to attain complete conversion in 7 hours. Interestingly, the reaction rate of the first ring reduction was higher than that of the second, what enabled the preparation of the hemihydrogenated bipyridine in acceptable yield. As mentioned above, bicyclic heterocycles are hydrogenated faster than monocyclic ones. Among important 5-membered heterocycles, pyroles and furanes can be hydrogenated, while imidazoles and pyrazoles are too stable and almost impossible to hydrogenate. In the case of indoles, it is usually the 5-membered ring that is hydrogenated first. This is an example of the selective hydrogenation of quinoline. In trifluoroacetic acid as solvent and with a platinum catalyst, the benzene ring was hydrogenated preferentially. In methanol, however, mainly the pyridine ring was hydrogenated. Such selectivities are, however, difficult to predict and must be rechecked for each new starting material. A few words on potential side reactions. Arenes often require harsher conditions than the hydrogenation of alkenes. Compounds containing strained or otherwise weak bonds might therefore undergo CC bond cleavage during such reactions. In this example, a benzocyclobutyl ether underwent complete hydrogenolysis upon treatment with hydrogen and a palladium catalyst at ambient conditions. Surprisingly, this side reaction did not occur with the corresponding acetic acid ester. The hydrogenation of anilines to cyclohexylamines is particularly difficult. The intermediate enamines are highly reactive and can undergo condensation with the product or the starting aniline, or may be hydrolyzed. Some of the common byproducts of aniline hydrogenation are shown here. Phenols can similarly yield various self-condensation products of the intermediate cyclohexanones. In this example, the hydrogenation of 2-trifluoromethylanilene in trifluoroacetic acid yielded, in addition to the expected cyclohexylamine, a cyclohexanol and a dicyclohexylamine. Because hydrogenation catalysts can also cause the dehydrogenation of alcohols and amines, hydrogenations in the presence of alcohols occasionally yield alkylated products, as in this example. Not only strained carbon-carbon bonds, but also weak carbon heteroatom bonds can be cleaved during catalytic hydrogenations. In this example, a terz-butyl ether underwent hydrogenolysis, despite being cyclic. The high reaction temperature probably also pushed this side reaction. Even non-strained carbon heteroatom bonds can undergo hydrogenolysis. When pyridine was hydrogenated with a large excess of supported platinum, the main product became pentane when increasing the temperature from 100 degrees Celsius to 150 degrees Celsius. Electron-deficient heteroarenes, such as pyridines, pyrazines, or pyrimidines, and the intermediates formed during their hydrogenation can react with water, alcohols, or amines. Isomerization of these adducts can then lead to a whole new set of byproducts, for instance amidines or amides, as in this example. The dienes formed during hydrogenation of arenes are often nucleophilic and form stable allylic cations with acids. These may then allylate the starting arene and lead to the formation of coupling products. In this example, hydrogenation of orthoxylene in the presence of a Lewis acid gave 27% of a substituted cyclohexylxylene. On this and the next slide there are some additional references which you can also find in the description of this video. The next presentation of this playlist is about the hydrogenation of arenes with the aid of soluble catalysts. Far fewer examples have been reported, but recently new carbene complexes have been found that catalyze such hydrogenations under mild conditions and with high functional group tolerance. So don't miss it.